So you took a you took the 2s electron and then moved it to the 3s. All right. When you think about it, here's the nucleus here, and then you have your 2s here, but the 3s is a big jump there, and it doesn't go to 3s, and it doesn't go to 3p, and NCl5 doesn't exist. It doesn't exist. Even though you could draw the Lewis structure for it, it doesn't happen because
Violates the rules.
well, it costs too much energy to jump it up to those orbitals versus a 3D orbital.
That's a good one.
Yeah, unfortunately. So the bottom line is this. Third period and beyond with empty d orbitals third period and beyond with empty d orbitals with the same n, I'll just say same n, can have expanded octet. Expanded octets means more than 8. Second period, like carbon, nitrogen, etc., these can never go beyond 8. And so second period, we know that the 2D orbitals are forbidden. 2D orbitals don't exist. Therefore, the max is an octet. We can never go beyond an octet. And so if you saw something like this, NCl5, no, that doesn't happen because it's nitrogen. Where are you going to put those extra electrons? Those extra electrons are going to go into the 3s, and that's unfavorable. This is more kind of experimental factual knowledge. You know, it just doesn't happen. You don't find NCl5. The next thing we're going to look at is the orbitals. You know, okay, we have the energy level diagram. Let's go back to methane. And what happens with methane is we got the 1s, nothing happens. But the 2s and the 2p, something happens. And what we said was we're going to promote one of the 2s electrons up into the 2p so that we get 4 unpaired electrons, which allows 4 hydrogens to come in and bond with it, right? And so the hydrogens come in here, one here, one here, one here, one here. Okay, now we want to take this a step further because do you guys know how to draw a p orbital? Actually, maybe this isn't the best.
The dumbbells?
Yeah, the dumbbells. Yeah. Yeah. Actually, you know what? I'm going to start off with something a little bit easier than this for drawing. You know, you have 2 dumbbells, that kind of stuff. Let's try this. Can you try NH2 minus? Draw the Lewis structure for NH2 minus. You know, have you heard of NH2 minus before? Amide, yeah. Or amide. Mm-hmm. Where have you heard it before? Yeah, in Chem 1A. So just go ahead and draw the Lewis structure. Tell me what the electron geometry is. Tell me what the molecular geometry is. Tell me what the angle, bond angle is. You do a 3D Lewis structure drawing for me. Yes. I mean, you could guesstimate the angle, too. Do the orbital energy level diagram. Yes, for nitrogen, and then show me how the hydrogens come in and bond to it. So are you done? Yeah? All right, let's take a look at it then. For the Lewis structure, let's try to draw 3D. What did you put in the plane? What did you put out of the plane?
Bonds.
Yeah, the bonds in the plane and lone pair. How did you show this lone pair coming out? The way I showed it is I just make it solid. And then this lone pair going in, I make dash. And then the angle here?
Less than 109.
Yeah, less than 109. About maybe 105. A 2-degree distortion per lone pair.
Can I ask a question about why you put the lone pairs there?
Why? I put it there because when I think about tetrahedral, I think of 2 in the plane, 1 coming out, 1 going in. And so here I have a single bond, a lone pair. And so I want to show the lone pair coming out. You know, some people do this to show it, but sometimes this wedge is taking us 2 electrons, so you got to be careful.
I thought we were doing it by most space.
Hmm?
With the unshared electrons, we kind of position it where we have the most space. I guess
The most space, the problem is with tetrahedral, I'd put 1 electron here, and then I try to put the other set, or the other pair on the opposite end of the molecule. And so if you try to do that, grab one, put one pair here and then figure out which one is the opposite end. So if I put one here, then I'd like to put one on the other side, but which one is the other side?
All of them?
They're all the same. And so no matter which position I pick, it's going to give me the same thing, so it doesn't matter. Here.
But you said the bonds are always in the plane.
Not always.
Okay.
Not all. Sometimes I'll throw a lone pair in the plane. That happens with ammonia, which we'll draw just in a minute. But let's just take a look at the energy level diagram. Look what you got here. 1s, 2, 2s, 2, 2p, 3, 1, 2, 3. And where do the hydrogens come in?
The first two.
The first two? No, it doesn't matter.
Doesn't matter that he's in the first two orbitals?
What doesn't matter?
Which of the p's you pick? The p's are going to be, one's going to be on the px, py, and the pz. So does it matter which one you pick? We could pick the last two. It doesn't matter. Or we can pick the first one and the last one. It doesn't matter at all. Let's just pick the last two. How about that?
Do they have to fill up in order?
Hmm.
Like before what we talked about?
Yeah, except what is the order? You do the x first, and then the y, and then the z?
So why did it matter before? Before, when we first started doing this, why did it matter that we had to fill them up in order?
We didn't. We didn't have to fill it up in order.
Oh, okay.
We could fill it up in any order we want.
So I could just go 2p in the middle, 1, 2p, the last one, 2, 2p over here, 3.
Yeah, it doesn't really matter because you know.
Is that literally what's happening to the electrons? They're just going wherever it's like 2p.
Exactly. It might fill the z first. It might fill the x first. It doesn't matter. Depends on the position. Except there's something not right about this.
It fills up the
Doesn't have the A is not charged.
Yeah, 2s moves 2p.
So what's going on? How many valence electrons does nitrogen have? 5. Hydrogen has 1 each. And so what's going on here? Yes, right. Do you know this nitrogen has an extra electron? Look at the formal charge on it. What is it? It's minus. Nitrogen normally has 5, but in this structure, it actually has 1, 2, 3, 4, 5, 6. And so this isn't a neutral nitrogen. This is a nitrogen with a negative charge on it. A nitrogen with a negative charge has an extra electron, which means we'll have 2 lone pairs, and 1 electron, excuse me, 1 bond here, 1 bond here. And that's what we get, right?
Over what you just said about, okay, so you said that nitrogen has 6 valence electrons, and that
Nitrogen has, normally nitrogen has 5 electrons, but nitrogen with a negative formal charge will have 6 electrons. It's like chlorine. Chlorine has how many valence electrons? 7. But chloride has 8. Because chloride has a negative charge. There's an extra electron. And so this is how we get 1, 2, 3, 4, 5, 6 valence electrons for nitrogen because it has a negative charge. That's how. It's got an extra electron.
you charge it that with 2p.
You see? Versus ammonia. In ammonia, what is the formal charge on nitrogen in ammonia? The formal charge? 0. That means it has 5 electrons. It's supposed to have 5 electrons. It's right. And so when we look at the valence shell, the 2s and the 2p, it has 5 valence electrons. 1, 2, 3, 4, 5. And so it has 1 lone pair and then 3 bonds.
So it's less stable?
No? Ammonia is more stable, but we'll talk about it later. Okay. So do you see that? Whereas, how about this? Do ammonium. And then we're going to come back to this. This is just another side. All right, let's do ammonium. If I do ammonium, ammonium has a tetrahedral structure that looks like this. Okay, how many electrons does nitrogen have in ammonium? I mean, actually have. It has an octet, right. But out of that octet, how many electrons belong to nitrogen using formal charge rules?
4.
4. So nitrogen has 4 electrons. It's supposed to have 5. That means this nitrogen is not neutral. This nitrogen has a plus charge. And so now when we look at the valence shell, the 2s and the 2p, we have only 4 electrons. Is this how it fills? No. What do? We know in this case we're going to promote a 2s electron into the 2p. Why are we doing that? So that we can form 4 bonds rather than 2 bonds.
So before you moved it, they were just, it was the 2s was full, right? And then you had only 2 x and y, the 2p with an electron, right? Before you added the hydrogen. And then essentially you took 1 electron from 2s and moved it to 2p, and that's how the 4 hydrogens.
Yeah. Basically, we don't have a full 5 valence electrons. We only have 4, so it's 2s2, 2p2. So one of the 2s gets promoted to 2p. You get that. And so when we do the energy level diagram, the energy level diagram is going to be dictated by the Lewis structure. When we see the Lewis structure, then we know how many electrons that particular atom has based on formal charge, and how many bonds and how many lone pairs it has. Using that information, then we can generate an orbital energy level diagram. The thing is, we don't generate the orbital energy level diagram first and then figure out what the Lewis structure is. We generate the Lewis structure first to figure out how the orbital energy level diagram must fill. And so it's a little bit backwards here, as you would think you would use this theory to predict. We don't. But one thing that we could do is, we know what the 2p orbitals look like, so let's take a look at the bonds here. Uh-huh.
We didn't know that it couldn't possibly exist until we did the orbital diagram, right?
Right.
So if I had just looked at the Lewis structure, I would have been totally convinced I was right.
Yes.
It wasn't until I got to the orbital diagram that I knew it was wrong.
Yes. Yeah. In that case, yeah, there would have been critical to look at the orbital energy.
I have a question.
Mm-hmm.
Okay, so you have the plus and you move the electron up. Why?
Otherwise, we can only form 2 bonds, which is okay. You know, maybe we'll only form 2 bonds. But if there's a possibility to form more bonds, right, then that's better. The more bonds we form, the better. The stronger bonds we form, the better. The reason is for stability, right?
Right.
Let me see, how do I turn this on? And so it's like this. Remember chromium? Originally we had 2 down here and 4 up here. This is the 4s, this is the 3d. But what we ended up doing is this, ad hoc analysis. You know what? A lot of people thought this is it. We're going to have 4 unpaired electrons. But when some physicists were doing some experimental measurements on the magnetic properties of chromium, they said it's impossible. 4 unpaired electrons is impossible. It has 6 unpaired electrons. And so what do we have to fix? Well, we got to fix this. Only way to explain that or describe it is to promote one of these 4s up to the 3D and then talk about the stability of a half-filled D subshell.
Promote, like we're looking at.
Promote means it's going to cost you energy. How much energy does this cost? It costs this much energy. Is that stable? You know, the thing is, okay, let's say you're lifting a weight up, you know, and you're just stacking weights up. And so you got to lift the weight, put it up on the shelf, lift the weight, put it up on the shelf, lift the weight. That costs you energy, right? And so if it costs you energy, is there any return? Like, you know, if you went to Las Vegas and you just, not that I promote gambling, but if you put a quarter into the slot machine, quarter into the slot machine, quarter, and you just endlessly feed quarters into the slot machine, and there's no payoff, why bother, right? And so the same thing here. If we promote this, then where's the payoff? Because we can't just be paying energy in without expecting any return. And I don't think you're going to last very long. I mean, if you knew you're guaranteed to lose all your money, would you be feeding quarters in? No, it's the same thing. There's got to be some kind of payoff. And so what is the payoff here? The stability of the half-fill subshell. Now we're going to just change the numbers here and reduce this. And now we're going to say, okay, this is the 2s, this is the 2p. Is there a payoff here? Well, what would the payoff be in this case? Well, if we took this electron here and move it here, that's going to cost us energy, but in return we're going to form twice as many bonds.
Okay, I have a question.
Mm-hmm.
You went from the 4s to the 3d. Isn't that too much energy spent?
No.
Uh-oh.
No, it's not. It's not that much energy. You know, quantifying the energy is difficult. This is where memorization comes in, because if we look at vanadium, it comes right before chromium. We get a situation like this, and we go, okay, I know about the stability of half-filled D subshell, so let's just promote both of these electrons up here to half-fill it. Does that happen? No. So we have to have some kind of factual knowledge memorized. Otherwise, we need to punch out numbers to make a comparison, because we can't just say, oh, it's small. You know, because somebody's going to ask you, well, how small? You know, what exactly is the number? Small is too vague. And so if we knew, you know, and it's too vague. It's not that big for one electron, but it's too big for two electrons. You know, at least we have some perspective there. Well, getting back to this, here we don't have to promote anything. This is just the way it bonds. So let's take this to the next step. The next step here is, let's look at these orbitals. I know the shapes of the orbitals. So for example, I have a p orbital here. I'm going to draw it like this. This kind of dumbbell shape thing. So here's a p orbital. And this p orbital has one electron. Okay. This is p. And then hydrogen has a s orbital. Here. Yeah, with one electron. And so this is what's happening here. When I look at the p orbital, a hydrogen comes into bond with it. Well, it's a hydrogen 1s orbital with one electron coming into bond with the p orbital on nitrogen. This hydrogen. And so this brings us to chapter 11. We're still in chapter 10, though, but I'm going to talk a little bit about chapter 11, and that is valence bond theory. Valence bond theory treats a bond as the overlap of two atomic orbitals. And so if I have a hydrogen atom here, there's a 1s orbital with 1 electron, a hydrogen atom here with a 1s orbital with 1 electron. If I bring these two hydrogens and have them bond together, what's going to happen is the two 1s orbitals will overlap. One electron's going to point up, the other's going to point down because of the Pauli exclusion principle. But when I look at the electron cloud here, the electron cloud here, the electron cloud here, when I look at the electron cloud where it overlaps is going to be higher density. There's just going to be more dots where the two orbitals are overlapping. And that's going to create the bond because the nuclei are going to be attracted to this region of concentrated negative charge density, or the electron cloud here. Okay. We call this an SS sigma bond. It's sigma. Sigma means that if we were to draw a line along the internuclear axis, just a line connecting the two nuclei, we'd see that the overlap occurs within that axis, the purple line here. And so that's what we call sigma. How to draw the sigma?
It's a person only.
Sigma like this?
Oh.
Yeah. That's sigma. So when I look at this, I do the same thing. I draw a line here that connects the two nuclei, and I look, these two orbitals overlap along the axis. And so this is called an sp sigma bond because I'm taking an s orbital on hydrogen and a p orbital on nitrogen and overlapping them to form an sp sigma bond.
I did not get that.
This is the p orbital here. This is the electron in the p orbital. And so what I'm doing is I'm just drawing the p orbital, which has these two lobes, and I'm putting the electron here. And then if I'm looking here, then a hydrogen comes in and brings another electron. And so the hydrogen comes in and brings another electron to create the bond. The bond is going to be generated when I look at the overlapping region. There's going to be a greater density of dots in the overlapping region, right? Which creates the chemical bond right here. And so this nucleus is going to be attracted to this nucleus because of the electron density here. In reality, the two nuclei try to repel each other. Does that make sense?
Why isn't it 2sp sigma bond? Why isn't it 2sp sigma bond?
2sp?
Because you have two hydrogen.
It is.
Those are two bonds, right?
Yeah, this is one bond.
So that
When you
little
write
circle
it.
you have up top, that circle right there, is that
This circle here is a 1s orbital.
okay?
And this dumbbell is a 2p orbital.
Okay. And you're signifying the hydrogen coming to the 1s?
Yeah, it's coming, the 2p orbital is this whole thing. And so it can only attach to one end or the other. And so if this is positive phase, it's going to attach to the positive phase here. This is usually negative phase here. The original wave function. And so technically this could be called a 1s-2p sigma bond because I have a 1s orbital on hydrogen overlapping with a 2p orbital on nitrogen.
But over there, you don't have the hydrogen on the 1s. The energy diagram, you have it on the 2p.
Okay, this is the energy diagram for nitrogen. The energy diagram for hydrogen looks like this. What's the valence orbital on hydrogen? 1s. How many 1s electrons do they have? 1. And so this is the energy level diagram for hydrogen. And what happens to this 1s orbital? What happens is nitrogen pokes in, nitrogen comes in and bonds to it. So nitrogen's contributing this electron to hydrogen. And so all I'm doing is I can look at it from nitrogen's perspective. When I look at it from nitrogen's perspective, here I am in a p orbital, 2p orbital, and hydrogen comes in to bond to me, like docking the space station. Or I can look at it from hydrogen's perspective. If I look at it from hydrogen's perspective, I'm a 1s orbital here, and then here comes the nitrogen. The nitrogen, it's not just nitrogen, it's nitrogen 2p comes in and block. Over here, it's a hydrogen 1s that comes in. And so I can be more descriptive like that.
So if we are looking at NH4 plus, then there are 4 possible bonds, so there could be a 1s2s sigma bond in there.
Yes. Right. Exactly. Come back to that. I picked this one because this one's easier. Now, where's the other 2p orbital? This is one of them. Where's the other 2p orbital?
On the other side.
Well, this is along the y-axis. Then there's going to be a 2p orbital along the x-axis. And so let's go ahead and draw that in. So the 2p orbital along the x-axis is going to have a lobe like this and a lobe like this. This is one orbital, right? And then I have one electron in that from nitrogen here. Do you see that?
Yes.
And so this is the 2p. And then what happens? A hydrogen 1s comes in. An electron from a hydrogen 1s orbital comes in. It comes in over here. Like that. In bonds. And so what do I call this? I call this a
1s, 2s.
Yeah, 1s, 2p,
Sigma bond.
sigma bond. So, my 1s, 2p, sigma bond.
So that arrow
All right.
represents the hydrogen, right?
Yeah. So I have one, which I'll call the py. A second one I call the px. Where's my pz? The pz is coming out. We'll do a different color here. The pz sticks out, so one lobe sticks out above and one lobe sticks in below, right? And that's going to have not just one electron, it's going to have 2 electrons. And so can a hydrogen come in here and link to the purple? No, because the orbital's already filled. It's got 2 electrons here. And so if a hydrogen comes in and tries, we'll get three electrons in this orbital. It's going to be a violation of
Mine's roll.
Pauli's exclusion principle. And so the green hydrogen's not going to come here. Right here. Right? And so this only has a capacity to bond 2 hydrogens. That's it. Are you okay with that?
I'm good, yes.
Okay, now, what about the 2s orbital? The 2s orbital sits, we'll just draw it in. Can a hydrogen come in and bond to the 2s orbital?
No.
No, because the 2s orbital is filled with 2 electrons. So we'll just draw the 2 electrons. So the hydrogen's not going to come in and bond to the 2s either.
Isn't it because of shielding too?
No, we just need space, that's all. If it's shielded, heavily shielded, then the bond's going to be weak. That's
But
it.
it can still bond.
But it'll still bond, right? All right, how does this look?
Good.
Looks good.
Now,
Complicated, except there's something wrong with this. With this.
Of course.
Of course, there's something wrong
Yes.
with this. What is wrong with this? It has to do with the angle. There's something very wrong with the angle. Can you tell me what's wrong with the angle? What is the H and H angle?
H and H, that's going to be
Well, what's the angle between the y-axis and the x-axis?
90.
90. So what's the H and H angle?
90.
90. What is the H and H angle that you just predicted? Less than 109. And do you see there's a problem? So one of those is right, the other's wrong. Which one is right, which one's wrong?
I would say the one we drew is wrong.
Which
This one is wrong.
Oh, we're doing both.
So it's because of
The Lewis structure.
The Lewis structure is right. This is wrong. This is wrong, unfortunately. Not completely wrong.
you just need to adjust the angle.
Yeah. And so there's one more thing that happens. And it's probably easiest to see this in, not this one, but in ammonia. And so this is the wrong bond angle. This is predicted to be 90 degrees. And so this is what happens here. We could do the same thing. You know, for ammonium, if we look at ammonium and we look at the valence orbitals only, because it was nitrogen, you know, we have the 2s and the 2p. And so when we look at this, we expect this one to be at a 90. So there should be an HNH of 90 and another one at 90. And so basically the structure that we predict using the orbitals would be, here's my nitrogen, I have a hydrogen here, we'll call that the Y. And then I'll have a hydrogen that I'll call the X, and then I should have a hydrogen that I'm going to call the Z, which is going to stick straight out of the board. What do those correlate with? Well, that correlates with the PY, the PX, and the PZ. You see that? And then the S, where is the S going to go? You know, because there's going to be hydrogen that comes into the 2s orbital. Well, this is a lot easier because the 2s is spherically symmetric. And so the hydrogen can come anywhere. Where do you think it's going to come in, though?
Down and left.
Yeah, down and left. It's going to try to avoid these other three, right? And so the hydrogen's probably going to come in and bond somewhere out here, like this. But it's not directional in the sense that, you know, just to try to minimize repulsions. Here. Well, this isn't very good because we know that electrons repel each other. And it doesn't give us the correct bond angles. And so we have to do something. And it's going to cost energy, but the return is going to be better. And what we have to do here is this. Remember we did the promotion to maximize bonding? Now we're going to add one more step to this. And the one more step is called hybridization. And so what we're going to do is we're going to hybridize these. We already talked about hybridization, but we talked about it in terms of resonance forms. This is hybridization in terms of atomic orbitals. And so we're going to hybridize the S and P atomic orbitals to generate new atomic orbitals, and these new atomic orbitals are called hybridized or hybrid orbitals. And so S and P atomic orbitals we hybridize to generate new hybridized atomic orbitals. And so how does that work? Let me show you here. All right, here are our normal orbitals. This will be the 2s, the 2px, the 2py, and the 2pz. Actually, I twisted the axis. I called that the y. It's okay. And so we see that these are orthogonal to each other. We'd have 90-degree angles, and then the s is spherical, so it's non-directional. What we do is we mix these four waves. Is it possible to mix waves?
Yeah. Or constructed and these were constructed.
And so if we can mix the waves, the wave functions, we generate these new waves, these new wave functions. And this is what we're going to get. And so if we take one S and three P's and then mix those waves, we can come up with what are called sp3 wave functions. sp3 wave functions are 1 part S, 3 parts P. In other words, it's 25% S, 75% P in the hybrid. The hybrid is a mix of the whatever you're mixing. And so these are called hybrid atomic orbitals here. And these, we mix 4 standard orbitals and we come up with 4 new hybrid atomic orbitals. And when we represent these, we'll just show one of the lobes, the major lobe here. And this is what we end up with. Does this look familiar? Yeah, tetrahedral. And so this is how we can generate tetrahedral angles. We don't generate it from S and P orbitals, we generate it from hybrid orbitals. And so we got to mix those existing orbitals to make new orbitals.
Wait, you said tetrahedral comes from hybridization?
Yes. And so for methane, that's exactly what happens. Methane's going to run into the same problem. You know, we should have 90-degree angles here, but we don't. We have 109.5-degree angles in methane. How do we get that? We get that by hybridizing. The orbitals, the reason we hybridize is to minimize the repulsions. And so here, let's take a look at carbon one more time. If we look at the energy level diagram for carbon, carbon has 4 valence electrons. We should only form 2 bonds here. But we promote, right? So we can form 4 bonds, but just promoting means the repulsions are going to be kind of big because 90-degree repulsions, are those favorable? No, they're too close, so they kind of want to spread out to 109. And so what we're going to do is promote and then hybridize. And so we mix all 4 orbitals to come up with 4 new orbitals, and these new orbitals are going to spread apart to minimize repulsions. And so these are called the tetrahedral sp3 orbitals. So we'll have here.
And the 3 is because it's 1 part S, 3 parts P?
Yeah. 1 part S, 3 parts P.
Oh, I see what you're saying. Okay. No, don't laugh.
So I need to redraw my drawing for amide and for all the others. When I draw these orbitals like that, that's wrong. Because what's going to happen is this.
Wait, don't.
Yeah, okay.
It's on camera.
Yeah, this is on camera. It's recording. So what's going to happen is this. I got too much repulsions here. I can minimize the repulsions by hybridize. Hybridize to minimize repulsions. When I hybridize, I'm taking 1 part S, 3 parts P. 1 part S and 3 parts P, mix those 4 waves, we're going to come out with 4 new wave functions, like this. Each one of these has an sp3 label indicating 25% S, 75% P. sp3, sp3, sp3. Now this is for carbon. Now carbon has 4 valence electrons.
How do you know it has 4 sections
For what?
on the orbitals?
4 orbitals?
Yeah.
How do I know? Because I'm mixing 4 orbitals. So 1, 2, 3 P's and 1 S gives me 4 orbitals. And so if I put in 4 waves, I'm going to get out 4 waves, basically. And then what do these orbitals look like? If I drew a carbon here, this is an sp3 here. This is 2 in the plane, 1 coming out, and 1 going in. And so these would be my 4 sp3 orbitals. They're equivalent, spherically symmetric. Each sp3 orbital looks exactly like the other. And then I put in my 4 valence electrons here. And so 1, 2, 3, 4. And then I'll bring in my hydrogens. The hydrogens will come here. one hydrogen will bond here. Boom, it's a 1s. Hydrogen comes here. And so what kind of bond did I just form? I formed a sp3, and then draw the axis. sp3 sigma bond. That's sp3 sigma bond here. Okay, then another hydrogen comes in here, bonds here, another one here, and one back here. And so hydrogen S comes in, a hydrogen S comes in, and a hydrogen S comes in. And so this is what we get. So this is called the orbital energy level diagram. Do you know what this drawing is called? Would be my valence bond drawing, showing the orbital overlap. Valence bond.
Okay, so what if you had nitrogen? Would you have 5 sp3s?
Oh, do ammonia for me. Okay, actually, this was nitrogen, wasn't this? Sorry. This was nitrogen here. But this wasn't nitrogen neutral, this was nitrogen with a plus charge. This is ammonium. I got mixed up because I was looking at the carbon.
Would it be the same method?
Hmm? Yeah. Ammonium and methane look very similar, except ammonium has a positive charge on nitrogen. Why don't you do ammonia for me, then? Ammonia. Okay, why don't you draw the... Yeah.
I know.
Oh, yeah.
He didn't tell you which one.
And is that on the 2 energy level? Into
Yeah, and it's equal to 2. I could put the 2 out here, you know, but most people don't.
And the energy level on that is between 2s and 2p?
Yeah, it's closer to the P's
Correct, right.
because
So
it's
the
weighted.
It's at the 75%, right?
Yeah, right. It'd be 75, so 25% below this, 75% above this, something like that, you know. Because energy is conserved. Well, the thing with ammonia is when we draw out ammonia, we know the structure looks like this. Well, what is the arrangement of the electrons? The arrangement of electrons is tetrahedral. Now, how the heck am I going to get a tetrahedral arrangement of orbitals? Well, the only way I'm going to get a tetrahedral arrangement of orbitals is if I hybridize to sp3. And so based on this, I know this nitrogen must be sp3.
well, that's how I got in trouble with the last one. Because I was like, it has to be this because otherwise it doesn't fit. So how do you know, like,
How you know is
to make that assumption?
yeah, it's just based on geometry. This one you aren't going to get in trouble. This one's always going to work. And so go ahead and figure it out. Do the orbital energy level diagram and then just write the valence bond drawing. Okay, we'll take a short break after this too.